An orange sky swallowed a parachute. Beneath it, the Huygens probe was falling toward ground no human eye had seen from space. The view below looked uncannily familiar. Saturn's largest moon, Titan, ranks second in size among all moons in our solar system, smaller only than Jupiter's Ganymede. Titan is so large that, alone against the Sun, it might easily be mistaken for a small planet, not a moon. Dutch astronomer Christian Huygens discovered Titan in 1655. The finding placed this distant moon into the astronomical record. That discovery began one of the longest observational histories of any outer solar system moon. Centuries of increasingly precise observation and patient watching. In 1994, Hubble infrared images finally revealed continent-scale bright and dark regions, but they still could not establish that seas existed. Eventually, astronomers established Titan's first decisive difference. It is the only moon known to possess a dense, substantial atmosphere. That atmosphere makes Titan behave less like an airless satellite and more like a small world with a genuine sky. Titan is also tidally locked to Saturn, one hemisphere permanently facing the planet, held there by gravity's steady pull. Titan takes about 16 Earth days to circle Saturn once, the same interval in which the Moon completes one rotation. Enormous size, a locked orbit, and an atmosphere no other moon shared. Together, those traits made Titan a solar system anomaly. So what did spacecraft find when they finally traded distant, watching for a journey into that hidden air? Titan's air is mostly nitrogen, the very same gas that fills most of the breath you just took. A smaller methane component changes the comparison. Titan's air echoes Earth's nitrogen-rich mix, but its carbon chemistry follows a very different path. At the surface, pressure is about 60% greater than at Earth's sea level, roughly what a diver feels 15 meters underwater. Titan's low gravity lets that atmosphere reach nearly 600 kilometers into space, about 10 times higher than Earth's. On the ground, Titan holds a cold near -179 degrees Celsius, a temperature that reshuffles the familiar roles of water and methane. At that cold, water behaves like rock, while methane can remain liquid, reversing the roles those materials usually play on Earth. Yet none of this was visible from outside. Early cameras aimed at Titan saw only a smooth, featureless orange ball, no ground at all. To map the hidden surface, scientists relied on radar and infrared observations rather than visible light. Imagine shallow water pressure without water, combined with cold that turns ice to bedrock and a view filtered through orange haze. Radar maps finally broke the stalemate. Broad, smooth basins and branching channels emerged where visible photographs had shown only haze. At -179 degrees, those basins could not hold ordinary liquid water. What substance was stable enough to collect there? The observations narrowed to one conclusion: Titan held surface liquid. On a world this cold, the next question was what kind. Cassini confirmed stable bodies of surface liquid. Titan remains the only world beyond Earth where such lakes and seas are known. But it isn't water. Titan's lakes and seas hold methane and ethane, hydrocarbons kept liquid by the intense cold. Even under sunlight, about 100 times fainter than Earth's, those hydrocarbons evaporate and condense into clouds, beginning a weather cycle built from different material. Those clouds eventually let go, and rain falls, carving channels that feed rivers, lakes, and vast methane seas below. Cassini mapped the largest methane and ethane seas near Titan's poles, separated by broad reaches of icy terrain. Toward the equator, the scene changes. Vast dune fields dominate broad reaches of dry terrain. Earth's water cycle moves one molecule among phases. Titan is less simple. Its carbon chemistry appears in liquid seas and likely organic-rich grains. Winds shape those equatorial dunes, but the grains are likely organic-rich rather than the mineral sand familiar from Earth's deserts. Their existence shows that wind and sediment transport operate even in a climate controlled by hydrocarbons and built on water-ice bedrock. Taken together, the seas, clouds, rain, and rivers form an Earth-like liquid cycle, built from hydrocarbons instead of water. The shapes looked familiar. The next question was whether familiar shapes also meant familiar physics. The answer begins with a force every falling drop and moving grain must obey: gravity. Titan's surface gravity is about 1/7 of Earth's. A spring scale that would register only a fraction of the same object's Earth weight. Lower gravity changes how a falling drop accelerates before Titan's dense air resists it. Familiar rain does not imply identical motion. It also changes sediment transport, so Titan's dark dunes cannot be read as simple copies of windblown sand on Earth. Saturn needs about 29 Earth years to orbit the Sun, so Titan's seasonal clock follows a far longer year than ours. Each season in the Saturn system lasts more than 7 Earth years, long enough for change to unfold across an entire human chapter. At any given location, mission studies suggest centuries can pass between methane showers. Titan's liquid cycle is active across the Moon, but highly intermittent at any one location. Long drought, then sudden rain. Beneath the dunes and dry channels lies not rock, but water ice, a crust of frozen bedrock standing in for Titan's stone. Titan also has few visible impact craters. The relative scarcity means its surface is young enough or active enough to erase impact evidence over time. Any explanation for Titan's landscape must satisfy 5 constraints at once: weak gravity, long seasons, rare rain, icy bedrock, and active resurfacing. Yet the surface left one deeper question unanswered: what lay beneath tens of kilometers of ice? Before the interior could be constrained, a probe first had to descend through Titan's atmosphere and reach the ground. For 2 hours and 27 minutes, Huygens descended through Titan's atmosphere before making the first, and still only, landing in the outer solar system. Those readings pointed towards something hidden below: liquid water sealed roughly 35 to 50 miles beneath Titan's frozen crust. Think of a sealed reservoir beneath thick ice. The water can remain liquid without ever appearing at the surface. Cassini amassed 127 close flybys over 13 years. Among their results, gravity measurements independently reinforced the internal ocean conclusion. The gravity data suggested this hidden sea isn't pure water. It's likely mixed with salts and ammonia, like a briny underground reservoir. A moon with liquid water sealed beneath its crust earns a special label. Scientists now call Titan an ocean world. That label matters because liquid water sealed beneath ice ranks among the most promising environments scientists study when searching for life beyond Earth. High in the atmosphere, ultraviolet light and energetic particles break methane and nitrogen into reactive pieces that can recombine in new ways. The result is a rich inventory of complex organic compounds. Some heavier products settle to the ground, placing that chemistry within reach of a surface mission. So Titan holds 2 remarkable layers at once: a buried ocean sealed far below, and a sky quietly manufacturing complex carbon chemistry above. What could a future mission test at the surface, where that organic chemistry is accessible? Those discoveries framed the next investigation: habitability below, prebiotic chemistry above, and evidence that might connect chemistry to biology. NASA selected a rotorcraft mission named Dragonfly to explore Titan and investigate its chemistry and habitability. Its rotors will carry the full science payload to varied locations. In flight, Dragonfly will collect atmospheric profiles and aerial geology images. One destination is Selk Crater, an 80-kilometer impact site where liquid water and organic material may have mixed for hundreds of thousands of years. Its value comes from time. Titan has run complex chemistry over planetary timescales that an Earth laboratory cannot reproduce. At each stop, Dragonfly's mass spectrometer will identify molecules and the processes that produce biologically relevant compounds, chemical evidence without assuming biology. A University of Arizona-led study asked how much biomass Titan's subsurface ocean might support if life exists there at all. If Titan's ocean holds any biomass at all, the study suggests it might total just a few pounds, barely a trace. Scientists do not consider Titan's surface a likely home for life as we know it. It is extremely cold and dominated by hydrocarbons. That surface verdict does not settle the ocean below. There, liquid water exists, but habitability still depends on available energy and chemistry. A few pounds is not a prediction of life. It is a model result, contingent on life existing and on specific assumptions being correct. Other instruments will monitor weather and surface variation, while seismic measurements look for subsurface activity. The mission widens the evidence without presuming an answer. Beyond that mission lie two questions that shape how we assess Titan's habitability and long-term evolution. What might be missing from that buried ocean, and could it hold the sustained energy needed for anything alive? Liquid water is only one requirement. Habitability also depends on a durable source of chemical energy. Models place the ocean between an outer ice crust and deeper high-pressure ice above the rocky interior. Whether usable energy crosses those boundaries remains open. Webb recently detected the methyl radical CH3, letting scientists observe an intermediate step in Titan's methane-to-ethane chemistry for the first time. Sunlight endlessly breaks methane apart, the way a lit candle steadily burns itself down to nothing over time. Yet methane persists. Some source must replace it over geologic time, but scientists do not know whether that source lies in the crust or interior. One mystery asks what the ocean can power, the other asks how the atmosphere is maintained. Neither yet has a definitive measured answer. That uncertainty guards against an easy mistake. Titan is not a frozen Earth. The resemblance is partial and process-based, not compositional. Precisely because its materials, temperatures, and gravity differ, Titan tests how weather and landscapes work beyond Earth conditions. In the end, Titan wears a landscape shaped like Earth's, yet every drop, dune, and cloud runs on foreign chemistry. Dragonfly's measurements will enter that unfinished story, but today the answer must stop where the evidence stops. Whether that ocean holds real chemical energy and what still refills Titan's methane sky remains unanswered. The mystery endures.